All right, so welcome back. Welcome back to this channel. In the last video, we have looked at a technique to actually make our model faster, right? So in this video, we are going to diverge from the topic. Again, we are going to get back to stable diffusion, and we are going to uh, we are going to develop stable diffusion not from scratch. We are not going to develop stable diffusion from scratch for now. But what we are going to do is we are just going to just dive a little deeper into the code, just get a little um, lower overview. We have had a like a high level overview, but we'll have a little lower level overview of what is happening inside stable diffusion. We'll just like all the things that that we have covered over the past few videos. We'll just revisit them, but through code, right? So we'll just get started. I have this little notebook. You can find it in my GitHub. In the description, I'll put the link to the stable diffusion repository, in which I'll upload all the code that will be writing for this series. So let's get started. So again, remember that I'll just revisit the topics that I have told you previously. So stable diffusion. So we basically build a unit, like which will just take in some noise. There's some random noise, and we can just find some features in the noise, and then subtract some other noise through which we could actually find some good images, and we'll have inference steps. So we'll just subtract this noise multiple number of times to actually get that image. And this is and one step of subtracting that predicted noise from the original noise is actually called the inference step. And we'll perform this inference step for a lot of times, and we'll hopefully get a good image, good looking realistic image. So that is the idea of stable diffusion, right? So and that is stable diffusion. And the idea of classifier free guidance also will be taking in prompts, and we could actually do conditional image generation. We could take in prompts, some embeddings, and just pass these embeddings through the unit, and would actually learn the relation between this not only the we will train the model to not only find patterns in that noise, but also make this output suitable to the prompt, right? It will find patterns, so it will find the relation between the prompt and the image. So which is actually pretty good. And I have also told you about classifier pre-guidance, in which we will have a prompt. We'll generate an image using that prompt, and we'll also generate an image for some arbitrary prompt or no prompt at all. And we can just get the weighted average to actually make sure the model does not we want the model to be both diverse and be obedient to the prompt. So therefore we'll use this classifier free guidance model to actually have a guidance scale through which we could control like how if you want to put you will use guidance scale to actually control how much importance the model has to give it to the prompt, right, over diversity. That is idea. Now let's go to the notebook. I'll try to provide you with as much as context as possible with each line of code. So let's get started. Right, in this so in the first I'm going to delete the runtime just to make sure that we can let's keep it. There's no need. Right, I'm going to first install this diffusers library, which contains like almost all of the models that we are going to use. So I'm going to import install these libraries. Right, that is first cell. Second cell, I'm going to import these libraries that we'll be needing: the logging library, pathlib library, matplotlib, torch, pytorch, stable diffusion pipeline, from the diffusers library. And then we'll also be needing a concatenation to actually concatenate like the we'll see about that, right? The actual image or the conditional image and unconditional image. We'll also be needing Hugging Face hub to actually get this model. We'll be needing PIL to actually display these images, and then through this line of code we could actually log into Hugging Face with our API key, such that we could actually use it for all the process. And if you run this cell, just go to Hugging Face. I have already shown you what you should do, but just go to huggingface.co, right? Just click on this, click on settings, and just click on access tokens. So if you click on access tokens, you'll get a secret code. Just click on copy, and just when you run it, just paste this API key that we have got, and it will say that login is successful. So that is how we can log in and import all these necessary libraries. And now here, and make sure while running this, make sure that your GPU is on, because we are using this line .2 CUDA, just to make sure that our model that are the code is running faster, right? And then so yeah, we are going to build a pipeline. We're going to create the pipeline of stable diffusion. So I'm going to say stable diffusion pipeline, which is going to be from this library diffusers. I'm going to say dot from trained. I'm going to call this. I'm going to input this model, this specific model, the this specific model, right? I'm going to specify data type, and we're just going to get this pipe, and we're going to make sure that we are using the GPU. And we could actually download all the model here. The output is that through this code we can actually download the models, right? And then now we'll import some more libraries that we'll be needing from transformers. Transformers is the library for language modeling, right? So we'll be importing clip text model, which will be the text encoder that we'll be using, right? I have given the context and the information of clip text model in the I think second video of stable diffusion, right? So how this loss function works and how like the language model works, right? And then we'll also be importing the tokenizer, just to make sure that we tokenize the values before passing them through the encoder, right? And after we have imported both of these libraries, we could actually call them. We could actually create objects of these classes, or methods that we have imported, right? I'm going to call the tokenizer. I'm going to say tokenizer equals to clip tokenizer, which will be this method, right? I'm going to say dot from pre-train. I'm going to call this function from that specific class. I'm going to say dot from pre-train. I'm going to give this model. So this is actually model, a language model, right? A trained clip encoder. It's already pre-trained, so that we could actually use it. Again, we are not going to train it by our own, because this is a little deeper. We're going to dive a little deeper into stable diffusion, right? And then I'm going to so this is the tokenizer. I'm going to import the text encoder, which will be same, almost same, but here we are going to use this class clip text model. Here we have used clip tokenizer. I'm going to call this model again, the same model, but of course we are going to use text model, right? Text encoder. This is just like the naive tokenizer, and this is the trained text model, right? And then now after running this, we have created our text encoder and our tokenizer. So we are good to go actually creating our conditional models. Again, here we are from diffusers, we are going to import both of these models. We are going to import auto encoder KL, which is essentially going to be the auto encoder that we'll be using. This will be the trained auto encoder that we'll be using to actually auto encode our images. Again, remember, before passing these images to our stable diffusion model, we are going to pass these images through auto encoder and get the latent space vectors, get the smallest vectors after the encoder. We just get this vector, and that vector will be the that vector will replace the place of this actual image, such that the actual computation power required is actually reduced. So that is the idea of auto encoder, right? So we are going to import this function, and we'll just are going to call that, and use a pre-trained auto encoder. Again, we are also going to import like a unit 2D a condition model, right? A conditional unit for stable diffusion. I'm going to call this. I'm going to create a method of this class. I'm going to object of this class. So we're going to call this method with this name or this model. And again, we're going to use the CUDA just to make sure that we harness the power of GPU. And then we're going to create the unit. So this is the VAE, variational autoencoder. I don't think it should be VAE, but okay, unit. I'm going to create a unit. So we're going to call this class. We're going to call this particular method, and this model, the stable diffusion V14 model. We're going to use the unit of this model. right? And then the subfolder, which will be unit. So this is actually like a huge folder, and then in that we're going to use this subfolder or sub model, right? So here until now we have imported our text tokenizer, the text encoder, the VAE that will be using to encode our images into smaller space, latent space for faster computation. We're also going to import unit for actually building the model, which takes in the noise and in the prompt to actually get our output image. And now the one thing that I want to tell you is inform you, one detail I want to inform you is while training, while training, as we move on through epochs. So in the first epoch, we are going to add or in the first training step, we are going to add lesser noise to the original image. So in the training time, we are going to have the training data set, right? So in the first earlier time steps, we are going to add lesser noise. And as we go on through time steps, as the time step progresses, we are going to add more and more noise, right? So that is the idea. And then we are going to use this class LMS discrete scheduler to actually take in the time step, right? And then predict the amount of noise that we want to give to the model. So that is the idea. That is why we import this class, right? And then we're going to import some of these other parameters like start and end, something like that. I'm going to call this class with these parameters, and then yeah. So I'm going to just call this class, and then we'll be setting some more parameters that will be needing for the use. So I'm going to specify the height of this image. So we're going to deal with 512 by 512 by 3 images, right? We're going to deal with those images. And then the inference steps, we're going to have 70 inference steps. That means we are going to subtract the noise. We're going to predict and subtract the noise for about 70 times. And then guidance scale is 7.5. So we'll be giving like 75% importance to the prompt. Then the batch size is going to be 1, right? Only 1 image for each batch. I'm going to create and after that, we are going to create a list of 2 prompts. The first prompt goes like a photograph of an astronaut riding a horse. So that is the first prompt. And the second prompt, an oil painting of an astronaut riding a horse in the style of Grant Wood. What is Grant Wood? I don't know. Let's see. It's probably a printer. Is right. I'm going to create both of these prompts, right? And then we're going to pass this. We're going to create a tokenizer on these prompts. So we're going to pass these prompts through the tokenizer. So this tokenizer actually trained on is already pre-trained. So this tokenizer is already going to assign like unique numbers to each words, right? And then the padding is going to be max length. So we essentially, no matter what the size of the word is, we're going to assume a max length. Here I think we have assumed it to be somewhere around 77 or something like that, right? And then so each word, so for example, this sentence is, for example, sentence has 10 words. So we're going to have 67 zeros as indicating that the sentence is already finished. But for making everything to be the same shape, we'll be adding this extra padding tokens. And we could just run it. We'll be adding tokenizer first, and then we're going to pass these tokenized values into the text encoder, right? I'm going to pass this text input to the text encoder, and then we're going to pass that through the text encoder. And don't worry about these small details; they don't actually matter much, but just make sure that you understand what is actually going on, right? Theory is better than details. So yeah. So and then next, I'm going to create a max length, which is going to be the like the shape. So we're going to have the text input, right? So the shape of this, so essentially we're going to extract the max length, which will be 77. And then I'm going to, just like we have seen in the last video, we're going to pass this. So essentially what we'll be doing is in classifier feed guidance, we'll just taken a prompt. We're going to pass this prompt to the unit, and we're going to get this image. And then we're going to pass in a empty prompt to this unit and get a image, and we're going to get the weighted average. So, and then that is the idea of classifier free guidance. But just to make sure that we are using a GPU. Like GPUs are good with parallel computation, right? Uh, Like computing things parallelly will help us to actually use GPUs. So that is why what we'll be doing is rather than just passing both of these separately, passing the prompts separately, we'll just like concatenate these prompts and get two outputs, right? So that is the idea of and like by using this, we could actually use GPU because we are performing parallel computation by concatenating both of these vectors. So essentially, what we'll be doing is we'll just get the like unconditional input, which will be this like empty string, and multiply that by length of prompts. So we can have multiple empty vectors or multiple empty strings, right? And then we are going to get these embeddings from this text encoder. Again, there will be going to be pretty arbitrary. So, and then after we have get this like unconditional embeddings, and we can just like concatenate both of these vectors, the unconditional embeddings and the text embeddings. So we're going to get like the text embeddings for these prompts, and then like unconditional embeddings for empty strings, right? And we'll just add both of these values, or not add, but just concatenate both those values into like a single matrix. And then I'll set the seed just to make sure for like reproducibility, just to make sure that we can run it and look at the same images, right? And then we're going to just assign the guidance scale to G. And then so hopefully you get the idea here what we'll be doing. So what we'll be doing is we'll just concatenate like the embeddings of both of these vectors for both unconditional embeddings and text embeddings. We're going to add both of these values into like a single matrix. And we're going to pass that through a unit, and we are going to get two separate images. So the output will be two separate images for each prompt, and then we could just split them, right? Split these images, output images. And then here we are going to create the random noise, right? That will pass through the unit. And then here we'll just call this set time steps on like we are going to set time steps for this scheduler. And then we're going to pass in the number of inference steps. So we're going to pass this parameter number of inference step to this scheduler. Again, this scheduler helps us to add the noise based on the time step. And then we're going to get the latence. We're going to multiply that by this noise, or this is just scalar. So we're just going to scale this latence by this factor, right? And then I'm going to do a bunch of things. For example, here I'm going to taking the scheduler, right? I'm going to call this function scale model input. So I'm going to scheduler.scale model input. I'm going to pass in like two latent vectors, because we want two latent vectors, right? Because for one for unconditional prediction and one for conditional prediction. So we're going to just multiply the by two, right? Just that will be the input, right? And then I'm going to pass I'm going to pass in like the input, the two latent vectors to this input. I'm going to pass in the time step, right? I'm going to pass in the embedding, right? The prompt. I think that is the embedding. Yeah. So yeah, we're going to pass in the concatenated embedding. So we're going to add both of these like text embeddings, right? We're going to pass that embedding, and then I'm just going to divide these vectors into two. So what I'll be doing is, again, as I've just like mentioned above, we're going to pass in the model two concatenated inputs that contains both the text embedding and the unconditional embedding. We're going to pass the concatenated version, and the output will be also be a concatenated version of images. So the images will be like concatenated, added. We're going to simply divide this output into two parts, and then the first part is going to be the unconditional part, and then the next part will be the uh like the actual part, the like guided part. And what I'll be doing is I'm going to follow this. So this will be the final prediction, right? Just have so this is the weighted average, just like weighted average. What we'll be doing is, after we have got two image outputs, so we have U and T, two separate image outputs. What I'm going to do is I'm going to say U plus G into T minus U. So here G is the guidance scale, right? It tells how much importance we should give for the like prompt, right? The higher the value of G, the more value this will have, and the lower value of and yeah, that is the idea, right? And then what we'll be doing is we'll just yeah, so we'll just update this latents. So as we go on, so this is just predictions over time space. So we're going to update this prediction. So essentially we're going to have multiple predictions, right? So I will take this prediction, right? I would just add this latents again, or I would just increase this latents noise. Right. So again, this is a for loop, right? So we're going to loop through like the time step number of times. We're going to loop through time step number of times, and we're going to prepare these latents for the next iteration, right? And then now it actually uh like pre-process these images, right? Simple pre-processing. We'll just decode. We'll first decode these images because the outputs are actually latent vectors, the sample latent vectors that are sampled or predicted, and we're going to convert them back into their original size by using the auto encoder. We'll use a decoder part now, and we'll just decode both of these values. And then now we actually look at this image. So this is the image you'll get for the first prompt, and then this is the image you'll get for the second prompt. So the first prompt is the photograph of astronaut riding a horse. So this is the photograph of an astronaut riding a horse, and this is the oil painting of an astronaut riding a horse in the style of Grant Wood. Right. So that is the idea. So that is the that's it for this video. Thank you for watching, and I'll see you in the next video. So goodbye.